This is a weekly summary of interesting news that is relevant for my lectures at the Eastern Switzerland University of Applied Sciences. My name is Thomas Bocek, and today we will discuss 6 topics. The first topic, it seems that this semester something is about homelab. So this is yet another interesting article about homelabs. It's the following here. So the author runs a self-hosted system with multiple machines. Here is a quick summary. It's a Dell server with dual Xeon CPUs and 256 GB of RAM as a primary Proxmox node, a Raspberry Pi 5 as a fallback ARM node, and a separate TrueNAS backup system with a Ryzen processor. And the total setup includes 88 cores, 296 GB of RAM, and 60 TB usable storage. The network uses MikroTik routers and UniFi Wi-Fi controllers to UPS units and monitoring through Grafana with Prometheus and InfluxDB. Everything runs on ZFS file systems with hardware redundancy through mirroring. And this is an impressive setup. And he also shows what happens when you run your own distributed system. SD card failures on the Raspberry Pi caused severe system slowdowns. SSH logins took minutes. Out of memory kills happens on ARM virtual machines despite having over 5 GB of free memory caused by incorrect kernel page size settings. The backup server completely deadlocked when ZFS storage reached full capacity. Garbage collection couldn't run because it needed disk space, but freeing space required garbage collection. The author received 30 error alerts in the morning from this backup failure alone. And this article demonstrates that distributed systems are complex and require constant maintenance when you own the hardware. Storage failures need monitoring and replacement. Configuration errors can kill processes even when memory appears available. Backup systems can log themselves out if not properly quota managed. The authors spent significant time debugging BIOS settings, mounting VM disks for recovery, and managing storage snapshots. In contrast, cloud providers handle these hardware failures, storage management, and low-level configurations automatically. Self-hosting means you handle physical failures, thermal management, power supply issues, and storage deadlocks yourself. I'm also self-hosting, but I do not have such an impressive setup, but it requires time for configuration. On the other hand, next week I'll report about the AWS outage, which also made many services like Docker Hub inaccessible. The next article is moving to a different provider. So whenever I see a cloud bill, I have the impression that every year it gets more expensive. And this article is a reminder to compare cloud costs from different vendors. Digital Society migrated their infrastructure from AWS and DigitalOcean to Hetzner Cloud and reduced costs by 76% while tripling capacity. They previously run their software as a service product on AWS using container orchestration, relational databases, and load balancer, and it costing them $450 monthly. Additional lightweight services run on DigitalOcean Kubernetes for $110 monthly, totaling around $560. And after migration, here they had a monthly bill of around $130. And here you see that the capacity also increased. The capacity previously had 12 virtual CPUs and 24 GB of RAM across both providers, and after migration to Hetzner, they got 44 virtual CPUs and 88 GB of RAM available for workloads, plus an additional 6 CPU and 12 GB RAM for control planes. 367% increase in both CPU and memory, although it depends also on the CPU generation, on the hardware generation, on the memory speed. So these are just rough numbers. And they chose Hetzner despite it requiring more hands-on management compared to managed cloud services. Their new stack uses Hetzner ARM shared virtual CPU servers with Talos Linux as the operating system, cloud native Postgres or PG for database management, replacing AWS RDS, and Kubernetes for container orchestration. All infrastructure is managed through Terraform and Helm with automated deployments. The main challenge was understanding Hetzner's network topology. Unlike AWS, availability zones, which allow low latency communication across zones with a region Hetzner location within the same network zone, have significant latency between them. And this made running multi-location workloads problematic and hurt performance. They solved this by using a single location with placement groups to ensure virtual servers run on different physical hardware for resilience. And this also shows the trade-off. They accepted more operational complexity and manual infrastructure management in exchange for dramatically lower costs and higher capacity. And another article which is linked here, it's a bit older, it's from August, 1st of August, it's the following here. It's about Unkey and it goes in the same direction. Here you need to assess which architecture is best for your services. Serverless is not always the best option. And Unkey, they offer an API authentication service. They rebuilt their entire API stack, moving from Cloudflare workers, serverless architecture to stateful Go servers, achieving a 6-time performance improvement. They previously ran on Cloudflare workers deployed globally across 300 points of presence, but latency issues forced the change. And we also covered latency in our distributed systems lecture. And the main problem was caching. In serverless, there is no guaranteed persistent memory between function invocation. So every cache read requires a network request to external storage. And Cloudflare's cache was consistently slow for reads. When building an API that needs sub 10 millisecond response time, this becomes impossible. Zero network requests are always faster than one network request, and no amount of external caches could solve this fundamental limitation. Serverless also created additional problems requiring more services. They needed Cloudflare durable objects, logstream queues, workflow, plus custom stateful servers on top. Each service added latency, complexity, and failure points. For analytic events, they built a custom buffering service to aggregate events before sending to ClickHouse, because the database cannot handle thousands of tiny inserts. For metrics and logs going to Axiom, they built a buffering service to avoid rate limits. They essentially built a distributed event processing system with multiple failure points just to work around serverless limitations. And after migrating to Go servers, batching becomes straightforward. Events batch in memory and flush every few seconds or when buffer is full. No additional services, no complex pipelines. The performance improvement was immediate and visible in their monitoring charts. The new architecture also enabled self-hosting, which was nearly impossible with Cloudflare workers runtime despite being technically open source. And the complexity tax affected development speed. Every feature required thinking about cold starts, runtime limitations, vendor lock-in, and workarounds. With stateful servers, they removed custom caching layers, homemade batching service, and complex log processing pipelines. The distributed system with many moving parts became straightforward. Serverless is designed for specific use cases like event-driven workloads and traffic spikes. And when your requirements fall outside that design, latency-sensitive applications, stateful operations, or data-intensive processing, you end up building workarounds that add complexity and costs. The architectural choice directly impacts system performance and operational complexity. The next article is the following here. It's about HTTP cross-origin protection middleware. This is a new addition in Go 1.25, and it's for CSRF protection, which eliminates the need for third-party packages. The middleware checks the fetch site and origin headers to determine requests origin and automatically rejects non-safe requests that are not from the same origin with a 403 forbidden response. I only briefly talked about cross-site request forgery in the lecture, focusing more on the cross-origin resource sharing with respect to load balancing and reverse proxy. We also focus on the bearer token for authentication that you store typically in local storage. However, cross-site request forgery should also be considered when building an application, especially when using cookies for authentication. Before the fetch site header, you had to carry a random generated ID, which was then typically sent in an input hidden field that had to match the ID, and this added some complexity. And the current approach with fetch site is much cleaner. However, the middleware only works effectively with modern browsers. fetch site header support is at 92% and origin header support is at 95%, meaning older browsers, pre-2020 browsers, they remain vulnerable. The fetch site header only works when applications use HTTPS with trustworthy origins. And when this header is missing and the middleware falls back to comparing origin and host headers, it has a weakness. It wrongly allows cross-origin requests from HTTP to HTTPS versions of the same host because the header doesn't include the scheme. Enforcing TLS 1.3 as a minimum version helps significantly. Almost all major browsers support TLS 1.3. They also support fetch site or origin headers. The only exception is Firefox version from 2018 to 2019, which didn't support fetch site and didn't send origin header for post request. And usage of these Firefox versions is currently at 0%, but the risk is non-zero. And the article clarifies an important distinction: cross-site versus cross-origin. Two websites are same origin if they share exact scheme, hostname, and port. Two websites are same site if they share scheme and registerable domain. So, for example, https example.com and https www.example.com are same site but different origins. The middleware blocks cross-origin requests, which is stricter in blocking only cross-site requests, and this prevents attacks from compromised subdomains under the same registered domain. However, before using this, you need to understand if you really need it. Authentication involves security trade-offs between bearer tokens and cookies. Bearer tokens in local storage are not vulnerable to cross-site request forgery, but vulnerable to cross-site scripting attacks because JavaScript can steal from local storage, but not if you have HTTP-only cookies. They cannot be accessed by JavaScript, protecting against cross-site scripting. If authentication happens cross-domain, cookies do not work and bearer tokens are required. So in this case, content security policies header can mitigate cross-site scripting risks by controlling which script can execute and setting the content security policy to default source self blocks inline scripts and only allows scripts from your domain. And the trade-off is cookies with cross-site request forgery protection as discussed versus bearer tokens with content security policy protection, where the choice depends on whether your authentication architecture is same domain or cross-domain. Very interesting article, and here is a list putting it all together. In my opinion, he forgot the point zero. This only applies if you have cookie-based authentication architecture. Nevertheless, very interesting article with lots of details in here. The next article is about a job interview. It's the following article here. The author nearly fell victim to a fake job interview scam where attackers posed as recruiters from a legitimate blockchain company. A freelance developer received a LinkedIn message from someone claiming to be a chief blockchain officer at Sympha, a real company with real LinkedIn profile having over 1,000 connections. The scammer sent a test project containing React and Node code base for evaluation, which is standard practice for tech interviews. The attack was sophisticated. The LinkedIn profile looked legitimate with proper work history and posts about innovation and blockchain consulting. The company had a full LinkedIn page with professional branding, multiple employees, and posts about transforming real estate with blockchain. They even used Calendly for scheduling. Before running the code with npm start, the developer asked an AI agent to check for suspicious code patterns, which detected the malware. The AI coding assistant found malicious code hidden in the server-side controller that would execute a full Node.js privilege when admin functionality was accessed. And it looked like this here. The malware is designed to steal cryptocurrency wallets, files, and passwords. Hackers have been using fake job interviews and platforms like Upwork and GitHub to infect crypto developers with malware. The attack chains use fake recruiter profiles on social media to share infected code base hosted on GitHub, GitLab, or Bitbucket that deploys backdoors under the pretense of a job interview process. And this demonstrates the risk of running untrusted code directly on your machine. Developers should consider isolating code execution in containers like Docker and using AI tools to scan for malicious patterns before running any code from external sources. And I actually did this as well. So I have here this Firefox plugin to mark here text, mark the selection. I didn't find the source code online, but when downloading the extension, I could paste the source code and ask AI if there is any malicious code inside. It was a rather small project, and the AI confirmed it's not, so it's legitimate. So that's why I'm using this tool. And as an alternative, I could have asked AI to write such a marker tool. It's only a couple lines of code, but if there is source code that is running and doesn't contain any malicious code, so that's good enough for me. The next article, it's the following here. And Paxos, the stablecoin issuer for PayPal US dollar, accidentally minted 300 trillion PYUSD tokens on Wednesday, then burned them all within 30 minutes by sending them to an accessible wallet address. Blockchain data showed the mint happened and the burn occurred 22 minutes later. The burned amount was worth approximately $300 trillion. And if valued with the dollar one-to-one peg, this would have been more than twice the GDP of every country on Earth combined. So they minted lots of money. Paxos stated that this was an internal technical error during an internal transfer, not a security breach, and customer funds remained safe. Following the incident, Aave temporarily froze trades for PYUSD after what they called an unexpected high magnitude transaction. The PYUSD price briefly dropped by about 0.5%, but maintained its dollar peg overall. Paxos has centralized control over token supply through minting capabilities, which differs from decentralized cryptocurrencies. The public blockchain made the error immediately visible and traceable through block explorers like Etherscan, showing both the transparency and the risks of on-chain operations. The quick burn responses prevented the excess tokens from entering circulation and destabilizing the peg. PYUSD has a market capitalization of over $2.3 billion, making it the sixth largest stablecoin behind Tether, USDC, and others. In the next lecture, in the upcoming lecture, I also accidentally minted 500 million OST meme coins instead of 50 million OST meme coins. So apparently this can happen to anyone. The last article, it's the following one here. The Department of Justice seized approximately $15 billion worth of Bitcoin in the largest asset seizure in the Department of Justice history. Bitcoin was held in cryptocurrency wallets owned by a man who oversaw a massive pig butchering fraud operation based in Cambodia. Charges of wire fraud, conspiracy, and money laundering conspiracy were filed against the alleged operator. If convicted, he faces up to 40 years in prison. The operator was identified as founder and chairman of Prince Holding Group, a multinational business conglomerate based in Cambodia that prosecutors said grew in secret into one of Asia's largest transnational criminal organizations. The Prince Group allegedly operates 10 scam compounds in Cambodia and runs businesses in more than 30 countries. The Treasury Department announced sanctions against the operator and more than 100 associated individuals and entities. Pig butchering is where the victim is encouraged to make increasing financial contributions over a long period. Here, a cryptocurrency investment fraud scheme where scammers contact victims via social media, building a relationship with them over time to earn their trust. The scammers then convince victims to transfer cryptocurrency with false promises that the crypto would be invested and produce profits. In reality, the funds are stolen from victims and laundered. The name comes from the process of fattening up a pig before slaughter. Scammers build trust over weeks or months before taking everything. And the Prince Group ran forced labor scam compounds across Cambodia where hundreds of people were trafficked and forced to work under threat of violence. Documents detailed facilities staffed with over 1,000 mobile phones controlling over 75,000 accounts on popular social media platform as seen here. The scam caused billions of dollars in losses to victims around the world. The operator and top executives allegedly used political influence in multiple countries and paid bribes to public officials to protect their criminal enterprise from law enforcement. So be skeptical of unsolicited contact on social media and professional networks, whether offering investment opportunities or job interviews. Verify identities through official company channels before downloading any files or transferring any funds.